Lecture 5, Processes in Unix. Okay, we have a brief introduction behind us now to the concept of processes and sort of a high-level overview of what they are and how they are supposed to work. And we mentioned also that a process may create other processes, and we can have the parent process is the one that's created it, and the child process, which is the one that's newly created. And we said that every process has a parent stretching back to init, or systemd, depending on your particular implementation. I also said that each process has a unique identifier, and in Unix this is referred to as the process ID or PID. Usually, as a user, you don't have to know it and you don't have to think about it. The most common scenario in which you may have encountered this previously is if you were trying to terminate a process that got stuck. If you were on the command line trying to kill it, you would use the kill command, perhaps with an argument like -9, and then you need the process ID to specify which one are you trying to kill. In this case, in the example here, you might have written kill -9 24601. Now, the init process will always have a process ID of 1. I don't recommend trying to use the kill command on init. For the most part, it will laugh it off, but if you are, for some reason, successfully able to do it some damage, that might end up just rebooting your system, and that's probably not what you actually intended. Okay, so imagine, if you will, that we have a process hierarchy that looks like this. Up at the top, there's always init, and there are, of course, a number of different processes, and there exists this tree-based relationship where every process has exactly one parent, and every process has its own unique identifier, and any process can have an arbitrary number of children. Here, bash with process ID 4310 has 2 children, and init has 3, and most other processes have only 1. Okay, and it is usually the case when you log into the system, this generates a login process, and the user's shell could be bash, could be C shell, could be anything else, is spawned from login. If you log in on the console, on the left side, it's spawned as a child of the secure shell daemon if you logged in remotely, and all of those things are processes, and they have this particular hierarchy. You can obtain a list of processes with the ps command, and this will actually show you what is actually going on, and we'll do that very shortly. When you issue a command like ls, which is listing the directory, or top, table of processes, hence top, the new process is created and the shell waits for it to be finished. It might finish quickly on its own, as is in the case of ls, or might wait for the user to tell it to exit, as in the case of top. When it does, control goes back to the shell, and you get presented with the prompt again, and you can then do whatever you want it to do next. And that, on its face, seems perhaps a little limiting. You might say, well, do I have to actually log into the system in a second terminal window to run 2 things at a time? The answer is no, and we'll see shortly a couple of ways to get around it. But first, let's demonstrate actually what happens when we are running these commands. Right, I have logged into one of the servers, and here we can issue a command like ls, and it will then list the contents of the directory, and that one's over with pretty quickly, and as soon as it's done, control returns to the command line where we can issue our next command. If I issue the top command here, this is the table of processes, and this will continue to run for as long as I let it. If I press the Q key, it will then exit, and it will then allow us to actually see what's going on and see what's running on the server. Now, the actual usernames will be blurred out when you actually look at it, because it's rude for me to expose other people's names in this manner, but this is going to show you the list of users, and process ID here is the leftmost column. If I want to actually list processes, PS will show us my current processes, and PS with the -ef command will show all processes in the system. If I just want to kill my own processes, ps on its own will be just fine. And ps-ef is more helpful for a system administrator who wants to actually wants to kill a rogue process, and you might spot a rogue process using the table of processes to see which ones are consuming a lot of CPU time. At the moment, nothing is really happening, and that's okay, so no action from an administrator is needed. Now, I mentioned that there are a couple of ways to actually do certain things in the background if you are so inclined. And one of the things you can do is add an ampersand symbol after the command that we want to issue. So we will search back in our history with Control-R for GCC, and here is a GCC command, and if I put a little ampersand here at the end, that will be dispatched to run in the background. Now, the compile that we asked for is very small, so it will be done very quickly. But what we'll be told is that the command will be started. We'll be told here in square brackets 1, it's the first background process that we have started, and it was assigned a process ID of 5652. Okay. When the process is finished, and you'll see that the next time you enter a command or anything like that, if I just press enter, it says first background process 1 is done, and it also reminds you of what the command was. This could have taken a long time, and that would be okay. One of the things about doing it in the background like this is that, well, things that are written to the console still appear on the console where this task was created. So if there are any outputs, you will see them, and it will kind of mess up what you see on the terminal in front of you. So maybe you don't want that. Maybe you don't want that at all. You can also, with lots of programs, I'll start one that I know produces a lot of output here. This one produces tons of output. We'll get to this example in a few lectures. You can redirect the output using an angle bracket, and we can call it on a PC output.txt, and oh dear, we appear to have had an unexpected crash. Bad things happen sometimes. We'll figure out how to debug that later, but I think the most likely explanation is I need to recompile that particular program for this computer. We'll see a little bit later when we look into some of the details when we start talking about libraries and threads and what have you, that when you compile, you have to recompile for different machines because the library versions might not be exactly the same. So let's try that and see if that helps us. No, it does not. Okay. We'll have to dig in and find out what's wrong at some later date when we actually get to that example. It just goes to show that some things can always be a little bit surprising. In any case, however, when we are creating output, we can run the read file one, which I know actually works. Then we can redirect that to output.txt, and then if we look in output.txt, then whatever the output of the program was, in this case telling us how to use it correctly, does in fact occur. So redirecting that is fairly common. There are lots of examples of where you might want to use the little ampersand thing to run things in the background. A common example of a command where I do this is along the lines of sudo service, if only I could type, xyz start with a little ampersand. Sudo means do this with super user permissions. Obviously doesn't work on the ECE servers, so this is in a different context where I actually do have rights to do this. And it starts the xyz service and allows me to enter my next command immediately instead of waiting for that service to be started, because what I'd actually like to do is watch the console log to see if there are any errors. But actually, the best way to run things in the background is with the use of the screen command. And the screen command is very, very helpful. It is good for interactive processes. Using the little ampersand thing, it's not interactive, so I can't type into the editor. But if I use screen, that's actually good. If you want, I can just start screen. It gives you a nice little introduction. And then it seems that we are in a little terminal window of our own. And so I can open a file, vim readfile.c. Highlighting is a little strange, but it's not a problem. If I wanted to then switch away from this without having to close it, I can detach the screen. The command for this is Control-A followed by the D key. And it detaches from the screen, and then I can screen -R to reattach to it and pick up where I left off, which is quite nice. That way you can switch easily between many different files and many different programs. The other thing that's great about screen is that it allows you to save the state of your work sort of in an intermediate state. Instead of saving the file and exiting and logging out, then I can just leave it open in the screen and then I can reattach it at some later point. That's also very helpful if your internet connection is not super stable, or if you don't want to risk losing anything in case Wi-Fi goes down or anything like that. If you have your editor open in a screen session, it doesn't matter if you lose connection. When you just disconnect from the server, then I'll simulate that by doing exit here, and then I can reattach, but I have to specify the same server. There are many machines that go by EC Ubuntu, and if I specified EC Ubuntu, then I could end up on a different server, but if I remember I was on EC Tesla 0, then when I reconnect, then I can reattach that screen, and we left off exactly where we were, cursor on line 23, unsaved changes, all that sort of stuff. So screen is very helpful in this regard, especially in a remote term where you might really be doing this over Wi-Fi at a coffee shop or something like that. Assuming coffee shops are open by the time that you were watching this, or if you're doing it from home and the Wi-Fi isn't super reliable, then you can do this without losing any work, and that's convenient. The other thing that I'll point out is that screen is somewhat complicated, so if you really want to read about it, if you use the man command, man screen, it really tells you everything that you could possibly need to know about this, and getting acquainted with how to read these things is very helpful. In particular, the command line options are nice. You can also take a look at commands that you can issue while you are in the screen itself, so like detaching, as I showed you, default key bindings here, as shown, can be used to do things like switching between windows, detaching a screen, scrolling up and scrolling down, all of that. You can learn how to do that by reading the man page, or you can actually edit the, you can actually look at the results in Google. It will also tell you. But probably, to get back on track, you want to know about actually creating a child process, and we're now finally ready to actually execute this and see what the code looks like and try it out. So the workflow in Unix is as follows. The parent process spawns the child process using the fork system call. Why fork? Because think like fork in the road. It's as if the road splits off at this point and the parent is going to take one direction and the child is going to take the other. If the parent process is going to wait for the child, there is a wait system call. There's actually two of them that we're going to take a look at, but there are two ways that you can wait for a child process. When the child process is finished, it returns a value with exit. The parent gets that as a return value of wait if it needs it, and you can throw it away if you don't care, but if you want to wait, it implies you're waiting for the child to be done, either to know that it is finished or to have the child process return a value. Either way is fine. So what does fork actually do? Well, fork creates a new process as a copy of itself. Spider-Man meme being most appropriate for this. The parent process runs up until it gets to the fork statement, and at that point the child is created like an identical clone of the parent. It is exactly the same in every respect. It is the same executable. It's at the same line. All the memory values are the same. It is a clone. It is a duplicate of the parent process. And both the parent and the child continue after fork. They will be able to, at that point, diverge and start to be different from one another. And the call to fork returns a value. If it's a negative number, it means something went wrong, fork has failed. If it returns 0, that is how we can tell that the process we're looking at is the child process. And if it's a positive value, i.e. not 0 and not negative, then this is the parent process, and the value we got back from fork is the child process ID. That maybe makes a little bit more sense when we actually look at the example. And you might be wondering then, well, how can one process start a different one if the child process is always a clone of the parent? And the answer to that is the exec system call, and there are certain variants of exec, but it is the child process saying, I don't want to be like you when I grow up, and deciding it's going to choose its own destiny. It's going to become a different executable program. This replaces its memory, its state, its executable with the new program, and it is optional. The child can continue to be a clone of the parent if that makes the most sense, but you can choose to be exec, and it's a little bit like in a Mission Impossible movie where the mask gets ripped off and it was Tom Cruise the whole time. That is like exec. It turns out that the process replaces itself with another one. At that point, programs can go their separate ways, or the parent might actually want to wait for the child to finish, if that actually makes sense. Let's consider a very simple code example, just demonstrating fork and having the parent and child processes write some things, and let's see what it does. Okay. To make this work, we have to include our usual libraries as well as the Unix standard library and then the sys/wait.h. Without this one here on line 4, you will just be told implicit declaration of the wait function, and we'll end up seeing that the program works as expected, but the warning is not nice and it'd be better to have it be correct. So in this example, we have declared int main with the incorrect arguments the compiler will tolerate, but it isn't optimal, so let's fix that. We declare a process ID variable. It's an int. Under normal circumstances, it's actually a PID type, so we could fix that as well, but it's just an int, so it doesn't matter. And we have a child status, which is also an int. Now, when we're executing this program, we start out by running it. So the first thing that happens is we allocate space for these variables, fine, main executes as per usual, and we get to line 10, fork is the system call, and that's where things start to change. So the parent process calls fork. The operating system creates a child process that is an exact clone of the parent, and we have now 2 processes, and both of them, their memory values are the same, and their execution state is the same. They're both at this fork statement. The key difference is the next thing that happens, and that is the assignment statement here on line 10. Because fork does some work and returns a result, the key difference is that we'll assume that it has succeeded. Fork returns a different value for the parent than it does from the child. The value that's returned to the parent is the process ID of the child. The value that's returned to the child is 0. And that's how in the if-else block down below we make a determination about who is what. So if PID is less than 0, it means there was an error, and we'll actually print out the error number if that helps us to figure out what went wrong. If PID is 0, that means this is the child process, and so we have some code here that says child executing. Fine. It will printf hello from the child process. It will skip over the else block and get to return 0. If it is the parent process, then PID is not less than 0 and it's not equal to 0, so we go into the else block and it prints parent executing. And then we have a wait statement here. And this is one of the 2 kinds of wait that we could actually take a look at. And there are 2 of them. There's wait PID and just simply wait. And wait PID, we wait for a specific child process. If it's wait without the PID, we are just saying we'll wait for any of the children that exist. This program has only one, so it's not really any different, but you can wait for a specific child to be finished, and we will then update this variable child status, and 0 for the flags is fine as the default. So when we are executing this code, you might ask yourself, well, what happens? So we create the two processes, and we'll see printf child executing, we'll see a printf hello from the child process, we'll see parent executing, and we'll see a printf this is the parent process, child returned, and then some status. Now, one of the things that we have to remember is that the operating system decides which process runs when. When we've created this child process after the fork call, it's not obvious which one is going to run. It could be either one. It could be the parent, could be the child, it could be neither of them right now because other things are running it, or it could actually be both of them in parallel if you have a multi-core system. So we can't make any assumptions about the order in which they're going to run. That accordingly means that we could see child executing appear first, or we could see parent executing as a statement appear first, and that should be a little concerning. We should want there to be a reasonable level of coordination between what's going on. However, we do have in this example a small amount of coordination, and that is the wait statement. And the wait statement here says that we are going to wait as the parent for the child process to be finished. That is, we can't continue to the statement that says this is the parent process and child returned a value until that's actually happened. So we do have a little tiny bit of coordination here within this program, and we need it for this to make sense. We can't print out the value that the child returned until the child has actually returned a value, so using wait here as a form of coordination makes sense. We're going to spend lots and lots of time talking about the concept of coordination when we think about concurrency as a topic. But let's actually get this started. Let's actually compile this and see how we do. I have forgotten to put the C in there, and then we are ready to go. So let's run it. And we will see parent executing, child executing, and then hello from the child process. This is the parent process. Now, one of the things that we will see if we run this enough times is we could see different orders of output. In this case, the program is fairly small, so we expect that it will be reasonably consistent, but you can't rely on that behavior. The only thing we can really rely on is that the statement at the end there, this is the parent process and child return 0, will happen only when the child process is done, because the only form of coordination that we have in our program is this wait statement here on line 22. Wait PID blocks the parent process, so puts it in the state blocked until such time as what it's waiting for, the child process to be finished, has occurred. Let's look at a second example where we're going to take a look at the workflow using exec. And once again, this shows a complete code example from int main all the way down to the return 0, in which we have a process ID, which is called by fork. And in this case, the major difference is that the child process calls exec, one of the variants of it, exec LP, which says actually instead of just continuing execution here, it's going to run the /bin/ls command, and that will list the contents of the directory, and then the parent process will wait for the child to be complete. The wait system call here is illustrated as being slightly different from wait PID, in that instead of 3 parameters, it now just takes the 1, and that is a pointer to the child status value, which we can then update, which will then be updated by wait. Okay, so the output looks something like this. If the directory contained only fork and fork.c, then it would show that, and then finally the parent process would print complete with status 0. As is expected, ls returned 0 because that makes a certain amount of sense. So if you wanted to represent that visually, when we get to the fork statement in the parent process, then things split off. If it's the child process, it takes the lower root here where exec occurs, and it does whatever executable we have asked for. And that gets to an exit statement. The parent process, if PID is greater than 0, just continues straight on to wait. It waits until the exit has happened from the child, and then, well, the parent resumes. Okay, what about exit? If I go back for a second, the previous example here didn't use exit anywhere at all. It had a return statement here at the end of main. That's fine. If you get to the end of main, it has the same effect as exit. The exit system call is just convenient because when you decide you are quitting, for some reason, perhaps in the case of an error condition, you might be nowhere near main. And it might not make sense to try to return a whole bunch of values indicating that you want to quit. You just call exit, and it's as if you immediately jump to the return statement at the end of main, and that is the final output for the process. Okay. If the program is going to exit abnormally, you can indicate that as well with your return statement. You could, as an exercise, modify the above code to create a child process that exits abnormally with an exit code of 1, and it will actually tell you so when you look at the results. The wait function does, incidentally, return the process ID of the child. Wait PID says it waits for a specific process, and the wait function generally is going to allow you to make a determination about which child it was that exited based on whatever its return value was. That's just in case you care. It's not used in the example. There's only one child, so we're not surprised by which one it is. Okay, I remind you that after fork, the parent process or the child process could continue, or neither of them, or both, so you can't make any decisions about workflow, or you can't make any output dependent on certain things running in certain order unless you have a mechanism of coordination of some sort. Okay, let's do a further example. We have a task that can be split into parts A and B, and you can use fork, as we've just learned, to create a child process. The child process should call this function execute B and return result to the parent. The parent process should call execute A and collect this result, and the parent should collect the results of the child using wait, and then put some console output out to your console. If no errors occurred, main should return 0, otherwise return -1. If an error occurs, it should be reported to the console, including some error number, so error 7 occurred, for an example. If more than one error happened, then report both. If both functions return 0, it means all is well, and the program should print completed to the console. This example occurred as a previous exam question, although it was intended for one of the exams where you write by hand in the gym, or if it was on a midterm, then in a classroom of some sort, as opposed to actually being written with the compiler. Okay, so here is the solution. It's a little bit of a struggle to fit it on the slide, but we managed ever so slightly. And we have some values: int child result, int parent result. So first thing we're going to do is call fork here, and that will get things started. If fork failed, return -1. Fine. If process ID is 0, then we're going to call execute B and just return the result immediately. If we are the parent, we're going to execute A and store that value in parent result, and then we will wait for the child to be done. Now, it is entirely possible that the child is finished before the parent. If that's the case, then no big deal. Wait just returns immediately with the result that's already available. So if the child is ready first, wait doesn't actually end up blocking our program. We just take the result and go. If the parent is finished first and it gets to the wait statement before the child is done, then actually the parent process is forced to wait. Okay, if the child result is 0 and the parent result is 0, everything went awesome, so printf completed and we're done, return 0. If the child result is not 0, then print whatever error was reported by the child process. If the parent result is not 0, report whatever error we have got, and then return -1. Okay, so not too complicated, just shows that we know how to use the fork and wait calls, and also how to structure our program so that the parent process does the right thing and collects results, and the child process exits when it's supposed to and doesn't continue doing things outside of this block where it's supposed to execute B, because you don't want the child process to try to go on into this area below. Okay. We'll take also a minute to make a slight digression from the topic of processes to discuss a denial of service attack called the fork bomb. The idea is that basically in a type while loop you call fork, and you can keep doing this until you end up crashing the system, or at least making it impossible to create any additional processes. As you can imagine, what you do is when you call fork, if you do this in a loop, each process, the parent and the child, now exists, and they will themselves call fork, and you end up with exponential growth, and it eventually crashes things and makes your system administrator very, very unhappy. So don't do this. A system configured to defend against this might impose some limits on, say, the number of processes you are allowed to create as a user, and or the rate at which a user is allowed to spawn new processes. And I want to say, don't attempt to do this on anything other than your personal computer at home. It is a denial of service attack and does count as misuse of resources on any system. Trying to do it could get you banned, and getting banned from using university computing resources is, shall we say, not conducive to completing your degree. Okay. UNIX systems, incidentally, do use signals to indicate events, and we've seen a couple of examples of that already. If you've seen me use the Control-C command on the console, that's actually a kind of signal. And signals are kind of like exceptions in that they are also used to indicate error conditions or to send a message. So a signal can be either synchronous or asynchronous. And synchronous is the signal occurs as a result of program execution. So at this line, there is a mathematical equation, and it involves a division. And if there's a division by 0 here, the signal is synchronous because you can point to this line specifically and say the signal occurred as a result of this line. It is asynchronous if it comes from outside the process and isn't necessarily associated with a particular line. If during execution I press Control-C, or one process is sending a signal to another, it arrives whenever it arrives, and we might know at what statement this program was executing when the signal arrived, but it's not tied to that line. It just occurred at that moment coincidentally. And signals are in the end really just interrupts with an integer identifier. So yeah, Gondor calls for aid. You send a signal, and hopefully it results in some action being taken on the other side. And hopefully that's not Theoden has changed his profile picture, thoughts and prayers. By default, the kernel will handle a signal that is sent to a process with the default handler. And there's a little table coming up with a set of default handlers, and there's some of them where the default is just ignore. There's some of them where it results in termination of the process. So there are a lot described in the standard, the POSIX 1990 standard. Signal hang up is hang up detected. Where does that come from? Okay, well, in the Dark Ages, before long before any of us were born, there were systems that communicated using the telephone network, long ago, there were UNIX systems that communicated with one another using the telephone network, and signal hang-up would be that the other side hung up the telephone connection. That maybe seems a little bit silly now, but that's the way that things actually used to work. Now, the signal hang-up has been repurposed in some contexts. Sometimes it's used to tell a process it should reload its configuration file, and you might see that on occasion where if you want to have your changes be applied, you send a signal hang-up to the actual executing process, and that will tell it reload your config file. It's just a strange convention. SIGINT, this is the keyboard interrupt. That's what happens when you press Control-C on the console, but you can, of course, generate SIGINT programmatically. There are lots of other ones, SIGQUIT, SIGIL for illegal instructions, SIGKILL is terminate process, SEGV, segmentation fault for an invalid memory reference, SIGTERM, terminate process, SIGCHILD is one of the ones that is ignored by default. And you can see when we get down to these advanced signals here down at the bottom, 20, 17, 18 as values, there are many different possible values. They're not fixed in the standard the way that signal hang up or SIGINT or SIGKILL is. And yeah, there are, as I say, default actions. In some cases, you are allowed to change that. You can choose to handle the signal, and you will find lots of programs, and we'll even see some examples later on, where your goal is to catch this SIGINT and then shut down cleanly. So recognize that the user has asked us to quit, do some cleanup, and then exit voluntarily as opposed to dying immediately. And a process can choose that for most but not all signals. If you want to do that, you have to register with the operating system, and we'll see in our topic about inter-process communication how exactly to do that. And we do some cleanup. It prevents things from being left, say, in an inconsistent state. In any event, a signal needs to be handled, even if handling is to ignore it. Otherwise, the signal just terminates your program unceremoniously. However, there are a couple of exceptions. The commands SIGKILL and SIGSTOP cannot be caught, blocked, or ignored, so in that sense, they are like the Terminator. They will not stop until you are dead. And that is just because a misbehaving program should not be able to disregard an administrator's command that says stop executing, and SIGSTOP is used for debugging purposes, and of course, that should also be able to work as expected. On the command line, if you want to send a signal, it is the kill command, even if you want to send something other than SIGKILL. And if you don't specify which signal to send, if you just type kill 24601, it sends a signal hang up to the process. And if no handler is installed for that case, it will result in termination. The process does have the opportunity, however, to catch it and deal with it if it chooses, such as clean things up. If the process is still stuck, you can force kill the process using SIGKILL, and to do that you do kill -9, and that sends signal 9, which is SIGKILL, instead of the default. And users are perhaps sometimes eager to jump to kill -9 because there's no such thing as overkill, but it's usually worthwhile to attempt a less severe version, just so the process does have an opportunity to try to clean up gracefully and exit in a normal fashion. Now, a signal is, interestingly, a form of inter-process communication. We are sending a signal from one process to another, even if it's just our terminal doing the sending. And this leads us into our next topic, which is about, well, how do we make processes communicate? And we should really spend some time to look into how to make that happen and to make it happen effectively. So that's our next topic, and I'll see you in that next video.